Welcome to Discrete Mathematics. Have you ever tried to organize a very messy closet? You naturally group similar items together so you can find them faster and they take up less space. In digital electronics, we do the exact same thing with messy mathematical rules using a powerful visual tool called a Karnaugh diagram. Let us dive in and see how it works. Now that we know what we are aiming for, let us define what this tool actually is. A Karnaugh diagram, often called a K-map, is a two-dimensional grid used to simplify Boolean polynomials. A Boolean polynomial is just a mathematical expression where variables are true or false. Instead of using long, tedious mathematical equations to simplify things, we place our rules into a special grid. By simply drawing circles around neighboring rules, we can instantly find the shortest, simplest version of our original messy rule. To understand how this grid works, we need to look at its design. The grid is carefully built using a sequence called gray code. In gray code, only one single bit, a 1 or a 0, changes as you move from one box to the next. Because of this strict one-bit change, any two boxes touching side by side or top to bottom are mathematically related. When we group the ones together, the changing variables cancel out. This visual grouping might seem like magic, but it is built on a solid mathematical foundation. The entire Karnaugh diagram system relies on a core rule of Boolean algebra, known as the adjacency theorem. This theorem proves that when two conditions are almost identical, the single difference between them can be safely ignored. The K-map simply turns this abstract algebraic theorem into an easy game of drawing circles. Let us look at the exact mathematical formula for this theorem to understand where it comes from conceptually. The formula states that AB plus AB naught equals A. Here, A and B are Boolean variables that can only hold a value of 1 or 0. B naught is the exact opposite state of B. This means if A is true and B is either true or false, the state of B does not matter at all. Only A matters. If the variable B changes, the outcome remains exactly the same. The K-map places these terms in adjacent boxes, so you can visually eliminate B. Before we move on to complex circuits, let us see this with a concrete, simple example. We have a digital circuit that turns on a light based on two switches, A and B. The rule is F equals A naught B plus AB. We want to find out if both switches are actually necessary. First, we map these terms onto a two-variable K-map. We place a 1 in the grid where A is 0 and B is 1, and another one where A is 1 and B is 1. Now that our ones are on the board, we look for adjacent boxes. By drawing a circle around these two adjacent ones, we are visually performing a mathematical factoring step. We pull out the common variable, which is B. The variables left inside the parentheses, A naught and A, represent the parts that change. In Boolean math, adding a variable to its exact opposite always results in a true statement, represented by the number 1. Continuing from our factored equation, we take the result from the previous step and substitute the number 1 back into our equation. This shows mathematically that the changing variable A has been completely neutralized and cancelled out. Our final simplified rule is just F equals B. Physically, this tells us that the light's operation depends entirely on switch B, making switch A completely useless. We can now build a much cheaper circuit using only one switch. Now that we have mastered two variables, let us tackle a more complex three-variable problem. Imagine a machine with three sensors, X, Y, and Z. It activates under four specific conditions, given by this long sum of products equation. We want to find the cheapest way to build this circuit by eliminating as many sensors as possible. Because we have three variables, we use an 8-box K-map. We carefully place 4 ones into the grid to represent our 4 specific activation conditions. With our ones placed, we look for the largest possible grouping. Notice that all four terms share the variable z without a not symbol. On the K-map, these four ones form a solid block of four adjacent boxes. By drawing one large circle around all four, we mathematically factor out the common variable z. The massive expression left inside represents all possible combinations of the remaining sensors, x and y. Let us finish simplifying this expression. Because every single possible combination of x and y is present inside our circled group, their specific values do not matter at all. They cancel each other out completely, leaving us with a constant true value of 1. The final simplified expression is simply f equals z. By grouping four boxes together, we eliminated two entire variables at the exact same time. Here is exactly what that three-variable simplification looks like visually. You can see the grid with x on the vertical axis and yz on the horizontal axis, ordered in grey code. The four ones we placed sit perfectly together in the middle, forming a 2x2 square. The large blue circle groups them all at once. Because the circle spans across both rows of x and both states of y, those variables are eliminated, leaving only z. Seeing this visual shortcut is great, but why does this matter in the real world? Digital circuits are built using physical electronic components called logic gates. Every term and variable in a Boolean expression requires actual wires, space on a silicon chip, and electricity to run. If an engineer builds a circuit using a long, unsimplified equation, it will be expensive, bulky, and slow. K-maps allow engineers to shrink these equations down before building anything. To wrap up our lesson, let us review the most important ideas. Karnaugh diagrams are powerful visual shortcuts that save us from tedious algebra. By arranging truth table outputs into a special grey code grid, we ensure that neighboring cells differ by only one variable. Grouping adjacent ones instantly cancels out redundant variables. Ultimately, this leaves us with the most efficient, cost-effective logic expression possible. You now have the tools to simplify complex digital circuits.